need to augment paths to check. So the first path I use is the A to B to D to G to Z, which is this one. And then to get the bottleneck capacity, you need to pick the lowest number out of all. So 5. So this becomes 0, this becomes 3, this becomes 4, and then this becomes 3 as well. After that, we need to find another path since there are still paths left. So the next one is the A to E to F to H to Z. So the lowest for the bottleneck capacity is 4. So we subtract it to the number here. It becomes 5. This becomes 0. This becomes 1. And then this becomes 2. This becomes 2. Next, we'll find another path if there's another available, which is the A to C to F to H to Z. So since the lowest here now is 1, so that's our bottleneck capacity. Then we subtract, becomes 4, this becomes 5, this becomes 0, and then this becomes 1. So after that, you need to check if there's another path that is available. But since there are no paths available now, since it's all blocked, then you need to add all the bottleneck capacity in order to get the maximum flow, which is then 5 plus 4 plus 1 is equals to 10. So 10 is the maximum flow of this. In order to solve this problem, we need to write in this format. So first is the visited, which is you will put the first vertex, which is the node A, and then put the unvisited, the rest on the unvisited. Next for the weights is the A is equals to 0 since it's the starting, and then infinity for the other nodes. Next is we're gonna check the value of each node that is connected with the A. So first is the B, which has a value of 2, and then the C, which has the value of 4, and then 9. So you put those in the weights accordingly, and then choose the lowest of the value among them, and then put it in the unvisited. And then you'll start in the next one, which is the node B, because that's the visited. So you'll start there again. And then the next step is check the value of the nodes connected to the node B, which is the node D, E, and C. So you're gonna add the weights. So the 2 plus 4 is equals to 6 for the node D, and then 2 plus 7, 9 for the E, and then since it's the lowest, so it's just 4 here since it's shorter. So you pick it's 5, basically it's 5. So you pick the lowest among them and then start from there. So the next is you put the values here accordingly, and then next put the C in the visited column. Then after that, we go to the node C and then do the same process all over again. So it's connected to F, node E, and then node D. So it's 4 plus 2 is equals to 6, and then 4 plus 6 is equals to 10, and then 4 plus 8 is equals to 12, and then write it accordingly. But since the value of E here is 10, it's higher than the previous value from here, you don't need to change it. After that, pick the lowest again, which is the D, and then put it in here in the visited column, and then put the unvisited here, and then start all over again. So here from the D, so it's 6 plus 2 is equals to 8, and then D to F is equals to 8 to F is equals to 8 as well. So you put the value here, and then after that you just pick one of them since it's both the same. So I pick the node E, and that's it. So the E that's the last part in the visited since there are no more, and this is the value of the nodes the shortest path of each node starting from the vertex.
Today we will be exploring Dijkstra's algorithm to find the shortest path in a weighted graph. Dijk's algorithm is a popular technique used in computer science to solve the single source shortest path problem. It helps us determine the minimum distance from a starting node to other nodes in graph. So let's start solving the shortest path in the given graph. So let's start with the node 0. Since node 0 has the shortest distance, we will examine its neighbors. Node 0 is connected to node 1 with a weight of 4, so we update the distance on node 1 to 4. There is the no direct edge from node 0 to node 4, so we leave its distance at infinity for now. Next, we move to node 1, which has the shortest distance of 4. We examine its neighbors node 2 and node 4. Node 2 is reachable with a weight of 8, so we update the distance to node 2 as 12. Node 4 is reachable with a weight of 11, so we update the distance to node 4 as 15. Now we move to node 2, which has the shortest distance of 12. From node 2, we reach node 3 with a weight of 7, so we update the distance to node 3 as 19. We can also reach node 6 with a weight of 4, updating its distance to 16. And we can reach node 8 with a weight of 2, so we update the distance to node 8 as 14. Next, we process the node 8, which has the shortest distance of 14. From node 8, we can reach node 5 with a weight of 6, updating the distance to node 5 as 20. However, the distance to node 4 is already smaller than what we would get from node 8, so we leave it as 15. Now we process node 4, which has the shortest distance of 15. From node 4, we reach node 5 with a weight of 1, updating the distance to node 5 as 16. Again, no update for node 8 as its distance is already smaller. Next, we move to node 5, has the shortest distance of 16. From node 5, we can reach node 6 with a weight of 2, but since node 6 distance is already 16, there is no update needed. We can also reach node 8 with a weight of 6, but again, node 8's distance remains the same. Now we process node 6, which has the shortest distance of 16. From node 6, we can reach node 7 with a weight of 10, updating the distance to node 7 as 26. However, no update for node 3 as its distance is already smaller. At the end of the process, we found the shortest path from node 0 to all other nodes. Here are the final distances. So the node 1 is 4, node 2 is 12, node 3 is 19, node 4 is 15, node 5 is 16, node 6 is 16, node 7 is 26, node 8 is 14. So let's trace the shortest path from the endpoints to node 0 using Dijkstra's results. First, for node 7 with a total distance of 26, starting at node 7, we look at the previous node, node 6, which contributed 10 to the total. From node 6, we move back to node 2, contributing 4. Then from node 2, we reach node 1, contributing 8. Finally, from node 1, we arrive at node 0 with a weight of 4. So its path is 7, 6, 2, 1, 0. So that's the shortest path for the node 7. Today we're solving a maximum flow problem using the Ford-Fulkerson method. The goal is to determine the maximum flow from multiple sources to the sinks in a transport network. Let's break this down step by step, covering the paths, bottleneck capacities, remaining capacities, and total flow at each iteration. In the first iteration, the augmenting path is node source 1 to node A and to node sink 1. The bottleneck capacity is the minimum capacity along the path, which is minimum 3 and 9 is equals to 3. So node source 1 to node A, 3 units used, so 0 remaining. So node A to sink 1, 3 units used, so 6 remaining. So the total flow after this iteration is 3. Next, we find a new augmenting path, source 2 to node A, to node D, to node sink 1. The bottleneck capacity is minimum 4, 5, 11 is equals to 4. So we update the flow. So node source 2 to node A, 4 units used, 0 remaining. Node A to node E, 4 units used, so 1 remaining. Node E to node sink 1, 4 units used, so 7 remaining. So the total flow is now 7. The third augmenting path is source 3 to node C, to node E, to node sink 1. The bottleneck capacity is minimum 11 to 7, so it's equals to 2. So we update the flow. So node source 3 to node C, 2 units used, so 9 remaining. Node C to node E, 2 units used, so 0 remaining. Node E to node sync 1, 2 units used, so 5 remaining. So the total flow increases to 9. In the fourth iteration, the augmenting path is node source 4 to node C to sync 2. The bottleneck capacity is minimum 2 and 1, so it's equals to 1. The update flow, node source 4 to node C, 1 unit used, 1 remaining. Node C to sync to 1 unit used, so 0 remaining. So the total flow becomes 10. In the fifth path, the source 4 to node D and to node sync 2. So the bottleneck capacity is minimum 3 and 4, so it's equals to 3. So the flow updates the node source 4 to node D, 3 units used, so 0 remaining. So node D to sync 2, 3 units used, so 1 remaining. So this increases the total flow to 13. So in the final iteration, the augmenting path is the node source 2 to node B and to node E and to node sync 2. The bottleneck capacity is minimum 6, 6, 2, so it's equals to 2. So the flow updates the node source 2 to node B, so 2 units used, so 4 remaining. So node B to node E, 2 units used, so 4 remaining. Node E to sync 2, 2 units used, so 0 remaining. So the total flow is now 15 and no more augmenting paths exist. So the maximum flow in the network is 15 units achieved after 6 iterations. So we will track each augmenting path, calculated the bottleneck capacity, the updated remaining capacities to determine this value.
This is my this is Mark Kelly representing his problem from maximum capacity from this discrete subject. And now I will begin my explanation. To find the maximum capacity of a path, you have to subtract the smallest or the minimum of the path chosen to the largest number. So ganito yun siya. So for our first path is from P1 to P4 to P5 to Z. Yan. Yan ang first path natin. Ngayon, i-erase natin itong mga numbers. Papalitan natin ng values. Yan, erase natin si number 6. Yan, erase natin yan. Then number 2, si number 6. Palitan natin ng 4. Yan, 4. Then ilagay natin yung smallest capacity or ang minimum capacity ng path. Yan, ilagay natin yan. Ngayon, ulitin mo lang yung ginawa mo ng first hanggang sa ma-cover mo ang lahat ng path. So, nagtaka kayo kung bakit hindi ako nag-umpisa sa A dahil since infinite naman to sila, so infinite capacity, so nag-umpisa na lang ako ito sa ating P1 since infinite siya, integer. So, diretso na lang. Next path natin is ito. Then, ang smallest is 3. So, erase natin yan. Then, ilagay natin siya dito. Nagtataka kayo kung bakit ko inilagay yung mga maliliit na numbers kasi ipa-plus natin yan sila mamaya. Yan, patuloy natin yan. 2. Yan. Next pass. So yan na guys, na covered na natin lahat ng mga possible ways na pwede nating magamit. Dito, nagtaka kayo kung bakit lang ako ito nagamit ito na part kasi wala na akong pwedeng mapagsisimulan na nagmula dito sa ating source. Yan, hindi ko na nagamit yan. So, ang total nito is ipa-plus na lang natin to sila lahat. So, ang total nito is 12. So, ang 12 na yan is, yan yung ating maximum capacity sa graph na to. Naman guys, isahanapin natin yung shortest path sa ating A to J. So, dito. So, since na-answer ako na, answer na lang at explain ko na lang yung sagot ko is, mag-uumpisa tayo ng AC to C to E, then E to J to H, then H to J. So, ngayon guys is, ipa-plus na lang natin itong mga numbers na to, itong mga nadaanan natin para makuha natin kung ilan yung value ng path nating nadaanan. So, 4 plus 3 is 7, plus 1 is 8, then plus 3 is ilan? Plus 3 is 11. Plus 3 pa isa. Is 11. Wait lang. Is 11. So, ito yung path. So, tingnan natin baka meron pang mas maliit. So, tingnan natin ngayon kung meron pa. Yan, umpisa tayo kay A to B, to Z, to E. Yan. So, ang total value ng path na tong green is 17. So, malaki siya guys. So, next path natin is itong orange. So, ang total value nito is 14. So, guys, ang smallest path natin or ang shortest path natin is itong yellow. Yan, yan, itong yellow. So, ito ang ating final answer.